Welcome to your unstable isotopes homework, everybody. Let's try question number 1. How many stable isotopes do each of the following have? So most elements have at least one stable isotope. This awesome periodic table that your teacher made for you, look at what it's got. Alright, let's just take this. Let's start off with Au. So we're going to find gold on the periodic table. Gold is down here on the periodic table, so let's just expand this some. So we're going to go here. So when I look here, what I see is these numbers here, they tell us how many stable isotopes. There's only one stable isotope for gold. It's gold 197. Whoops, I didn't mean to do that. Hang on a second. Okay, so for gold, there's one. Let's look at mercury, and then I'll let you guys figure it out on your own. So for mercury, which is Hg, let's see, I have 1, 2, 3, 4, 5, 6. I have 7 stable isotopes of mercury. So for Hg, the answer is going to be, the answer is going to be 7. And you can figure out the rest of them. They go the same way. All right, let's try number 2. Which of the following best describes the following isotopes? All right, so let's see. Stable, too many neutrons, not enough. Let's try. So we'll start off with this rascal right here, sulfur 36. Now please notice in isotope notation, the number on the bottom is the atomic number, and the number on the top is the atomic mass of that particular isotope. So let's go look at sulfur. So we have sulfur, and here we have sulfur. And when I look at sulfur, what I see is the question we're asked is sulfur 36. So if I look at sulfur 36, sulfur 36 is one of the 4 stable isotopes of sulfur. So for here, I'm going to put A. It is stable. Let's try the second one, silicon 27. So let's find silicon, which is right here. Let's make it a little bit bigger. Okay, so we're looking for silicon 27. Here's silicon. Notice it's 28, 29, and 30 of the 3 stable isotopes. So 27 means it does not have enough neutrons. That's what that would mean, because the mass is too low, and it's the number of neutrons that gives it its mass, since we can't alter the number of protons. So the answer here then would have to be C. It does not have enough neutrons. Now the next one is radon 222, and that's element 86. So let's see what we've got here. Radon. Well, here's radon, but what I want you to notice about radon is this. The largest element that has any stable isotopes is bismuth, element 83. Once you get to 84, 85, 86, and everything up to 118, you'll notice there are no stable isotopes. And that's because the nucleus is too large. You really can't glue more than 83 protons together with neutrons. Once you get beyond that size, the neutrons just can't hold it together, and it eventually falls apart, producing alpha particles. So the problem here is our nucleus is too large, and that would be choice D. And the next one, copper 66. Well, here's copper right here, and let's expand it. We're looking for copper 66. I notice copper has 2 stable isotopes, 63 and 65. 66 would be heavier than the largest stable isotope, so therefore it would be too heavy, meaning it has too many neutrons. So let's shrink this back down, and we'd say the answer here would be B. Well, that's a D. Whoops. Excuse me, I'll erase that. Okay, let's try again. That's not. Here's how you make. Oops. Here's how you make a B. My bad. Sorry about that. Let's try number 3. Identify the decay particle emitted by isotopes with the following reasons for instability. Well, if the problem is you have too many neutrons, then you've got to get rid of a neutron. And let me show you basically what happens. So if we have a neutron which is by itself or is in a large nucleus with too many neutrons and is somewhat isolated from other protons, it becomes unstable, and what it does is it will emit or spit out a particle that is an electron. It has a mass of 0 because electrons have, like fleas on a dog. and it has a -1 electrical charge. And remember, when you emit something, this here is being removed from this here. We're always emitting it. It is leaving the nucleus. So if I take 0 and take this away, well, basically a neutron has a mass of 1 and an electric charge of 0. So if I take away 0 from 1, I still get 1. And if I take -1 away from 0, 0 minus -1 is +1. And a particle that has a mass of 1 and a charge of 1 is called a proton. So what happens in this type of nuclear decay, which is called beta decay, is that a neutron spits out an electron and decays into a proton. So let's go back to that problem and see what we've got here. So the answer we have here then is this one spits out an electron, which will be symbolized with lowercase e, 0 mass, and -1 electrical charge. Well, what if the nucleus is too big? And by too big, I'm talking 84 or more protons. Let's see what we get then. When you have a really large nucleus, one that has, let's say, 84 or more protons in it, you just can't hold it together no matter how many neutrons you put in there. Now you would think it would just spit out an individual proton, but it turns out a proton is not the most stable thing you can spit out. So instead what it spits out is a particle that has 2 protons and it has 2 neutrons. So it's essentially the same thing as a helium nucleus. Now since this was the first type of particle radiation to be discovered, it was called alpha for first, so we call this an alpha particle. So this here is called an alpha particle. And if we want to write a shorthand notation for it, we're going to treat it like we're going to make isotope notation for it. So what we do is we say, well, it has basically, it's identical to a helium nucleus. It has a mass of 4 and a charge of +2. So this is how we write alpha particle. And remember, that is being emitted from this. So this is going to lose 2 protons and a mass of 4 whenever it gets emitted. So let's go back to see what we had here for our question. So it looks like the answer to that one would be an alpha particle, He, 4, and 2. What if your problem is you don't have enough neutrons, so you need to gain neutrons? You need to take a proton and turn it into a neutron. That's what you need to do. Let's see how we do that. Okay, so what I have here is I have a proton, and I have too many protons, so I need to turn it into something else. I need to turn it into a neutron. Well, what do you spit out? You've got to get rid of some positiveness. So what you spit out is a very interesting particle called a positron, or an anti-electron. It is identical to an electron in terms of its mass. It has a mass of 0, but in this case it has a charge of +1. It has the exact opposite charge of an electron. So this is a form of antimatter called a positron or an anti-electron, whichever you prefer. So in this case, the nucleus is going to lose 0 mass, but it's going to lose a +1 charge. And essentially what was a proton will spit out some positiveness and decay into a neutron, and therefore the isotope will lose a proton and gain a neutron, and therefore hopefully gain some stability. So let's go back to our homework. And so the answer there was a positron, which has a mass of 0 and a charge of +1. Alright, let's see what we got here. Number 4, identify each of the following as an alpha electron or positron. Well, heck, we just did that, didn't we? So let's see. This has a charge of 0 and a mass of 0 and a charge of 1. That's right here. That is what we call a positron. Sorry for the messy handwriting. Now the next one has a mass of 0 and a charge of -1. You know what? That's called an electron. Electron. And the next one is called an alpha particle. So it's useful to know both the name and the chemical formula, the isotope symbol for each of these. Alright, well, let's just keep moving things along here. Alright, what type of decay particle will the following emit? So what we have to do now is we have to look and determine what kind of a problem the nucleus has. Alright, so is it too big, is it too small, or does it not have enough neutrons? So first we're going to look at this one here, Br35. So let's find bromine, in case you had a hard time finding it. It's over here. It is one of the halogens. Let's make it a little bit bigger here. Let's see. Alright, oh, you know what, I forgot which one we were looking at, so let's just see what we have here. What we're trying to find is bromine 78. Okay, so bromine 78, if we look at bromine, we see that 78 is below that, so in this case, we don't have enough neutrons, and since we don't have enough neutrons, if you don't have enough neutrons, what is it that you do? If you don't have enough neutrons, you emit this, and this is called a positron, which is right here. So you emit a positron when you don't have enough neutrons. Let's look at what our next one is. The next one is Krypton 84. Let's just bring that up. Krypton 84. Krypton. It sounds very radioactive, but in fact, if we look, here's Krypton. Here's 84. That means it's a stable isotope because these are all stable isotopes of Krypton, and 84 is stable. So therefore, and it only has 36 protons, which doesn't make it unstable. So this is a stable isotope. So when we go down here, it's not going to emit anything. So the answer in this case is going to be D. It will emit none. Let's try the next one. Einsteinium 252. And that's atomic number 99. So let's bring this up here. Einsteinium's way down on the bottom here. Let's keep going. Oh, here's Einsteinium right here. Let's see. So here's 99. What we notice is, since it has 99 protons, that means it is too large. The nucleus is too big. And when the nucleus is too big, what you emit is an alpha particle. And our last one here is going to be iron 59, so element 26 with an atomic mass of 59. Let's take a look at what we got here. Alright, so here's iron, and we notice it should be 54, 56, 57, 58, and what we had was 59, and that means that it's more massive than it should be. It's too big, and when a nucleus is too big, it gives off an electron, which would be right here, choice B. I did it again. Alright, let's try that again. What's with me today? Okay, that's not a B. Whoops. That's a B. Man, I don't know what my problem is. Alright, we're doing great here. Let's keep going. Alright, give the daughter isotope that would be formed if the nucleus in each of the following emitted a positron. So let's just consider what's going to happen here. Magnesium is going to spit out a positron. And a positron looks like this. So what we're going to spit out is a particle that has a mass of 0 and a charge of 1. When something is emitted, it leaves the nucleus. So this particle here is going to leave this particle here, taking with it 0 mass and taking with it 1 unit of positive charge. So therefore what's left behind is 22 minus 0 is 22, 12 minus 1 is 11, and element number 11, if I look on my periodic table, is the element sodium. So that's the daughter isotope, sodium 22. Let's try the next one. Chlorine 33. I'm going to take 0 away from the top and 1 away from the bottom. That's what happens when you emit a positron. So therefore, the top stays 33, and the bottom goes down to 16. And if we look it up, unless I'm mistaken, that's going to be sulfur. Element 16, yep, it's sulfur. Alright, so let's just put an S here for sulfur. Now the next one is nitrogen 13. So again, the top is going to go down by 0, and the bottom number is going to go down by 1. So we still have 13 mass units, but now we only have 6 units of positive charge, and element number 6 is carbon. Now you notice that's not the most stable isotope of carbon. No one said it is, but that's what happens if this particular isotope here emits this particular particle here. Well, we're doing great. Let's just keep going here. Now, in this case, these isotopes are undergoing electron emission. So the trick here is to make sure you know that electrons look like this. The isotopic symbol for it is that. And emit means to get rid of. So when we emit one of these, the top will go down by 0 and the bottom will go down by -1. So when you subtract -1, it's the same as adding 1, because what was a neutron becomes a proton. So in this case here, for 81 will stay 81 because I take 0 away from it. But when I take -1 away from 34, I get 35. And if I look up element 35 on the periodic table, I'll see that 35 is bromine. So what we have now is bromine 81. Br, that is. Okay. Now the next one is rhenium 189. So I'm going to take 0 away from the top, and I'm going to take -1 away from the bottom. So the top will stay 189, and the bottom will become 76. Now I just had to figure out what is element number 76, and to be honest, I don't know. Is it terbium? I'm going to take a guess. I'm looking for 76. Where the heck is 70? That's not 76. Where is 76? Oh, 76. There it is. It's osmium. I can't believe I said I thought it was a terbium. So it's osmium. Alright, let's keep going here. So that is going to be osmium 189. And finally, I have neon 22. So I'm going to take 0 away from the top, leave me with still 22. I'm going to take -1 away from the bottom, which gives me 11. And element 11, I do know that one by heart, is sodium. Well, let's just keep going. So in number 8, we're going to give off alpha particles. So now remember, an alpha particle, you know what, let me move this up a little bit. An alpha particle looks like this. It looks just like a helium nucleus. It has a mass of 4 and a charge of +2. And I'm taking that away from each of these 3 isotopes. So when I take 4 away from this, what I get is 232. And when I take 2 away from 93, what I get is 91. Then I look at my periodic table and say, who is element 91 anyway? Element 91 is right here. It is protactinium, I'm sorry to say. But I just need to know that the chemical symbol for it is Pa. So let me shrink this periodic table down and get out of the way. So it's Pa. Alright. There we go. Pa. The next one is radon 222. So the top is going to go down. 22 is going to go down by 4. So 222 minus 4, that is 218. And I lose 2 units of positive charge. So instead of 86, I'll have 84. And element 84 is polonium. That one I happen to have committed to memory. I think, let me go double check it. I could be wrong. Is 84 polonium? Yes, 84. There it is. That's polonium. Good job, Eric. Alright. Now the next one is fermium 258. So that 258 is going to go down by 4. So the mass goes down by 4, giving me 254. And the bottom number, 100, is going to go down by 2. So that's going to give me 98. And you would think I know what element 98 is. I don't. It's one before Einsteinium. I know that. Let's see what it is. Element 98 is, there it is. It is our old friend Californium. CF. So we're going to put a CF here. Hey, look at this. We're almost done with our homework. Alright, let's move this up a little bit more. Hang on. Okay. So we've got here is now number 9. We're going to bring it all together, folks. Alright, determine the type of instability, then give the predicted daughter isotope. So the first one I have is nitrogen 17. So we find nitrogen, which is right here. Let's make it a little bit bigger. So we're looking for nitrogen 17. I notice that the 2 stable isotopes of nitrogen are 14 and 15, and since we're 17, it's too large. So the problem is it has too many neutrons, which means if you have too many neutrons, you're going to give off an electron. So if I take an electron away from it, 17 goes down by 0, so that stays 17, and 7 goes down by -1, which makes it go up to 8, and element number 8 is oxygen. Alright, let's try the next one. Alright, we've got molybdenum 91, so let's just find molybdenum on the periodic table. I'm going to say that again because I like to say molybdenum. Molybdenum 91, if you'll notice, does not have enough because, well, I'll make it a little bit larger. Whoops, that's not it. So if you look at molybdenum, it 92, 4, 5, those are all stable, but 91 is below the stability, below what we call the band of stability, and therefore it doesn't have enough neutrons. And when you don't have enough neutrons, what you give off is a positron. So a positron, remember, is like an electron, has a mass of 0 but has a charge of +1. I'm going to take that away from 9142. So 91 minus 91 is 91. And 42 minus 1 is 41. And element 41, if we look right here, is niobium. And we are almost done with our homework. Let's look at the last one here. Alright, so we have thulium 90, well, 232, 90. 90 is bigger than 84, or bigger than 83. So that means it's too large. The nucleus is too large, and when things are too large, they give off alpha particles. An alpha particle is identical to a helium nucleus. It has a mass of 4. It has a charge of 2. And I'm taking that away from this isotope here. So the top is going to go down by 4. So 232 minus 4 is 228. And 90 minus 2 is 88. And if you look up element 88 on the periodic table, you're going to see that that happens to be the element radium. Well, I hope you enjoyed this homework as much as I did. It was awesome. Please refer back to this anytime you get confused. Students sometimes have a difficult time with this, but I think you'll do fine.